guys, once again we are here and come up with a new part, that is important terms in magnetism. So these important terms, what are these important terms? Basically, I'm not revealing that thing, but basically what I'm saying is that you should know about these terms before proceeding in magnetism. So what are these terms? I'll be discussing it in this part only. So for that, let us see. Let's proceed. So guys, important terms in magnetism and magnetic field. Now in this part we are going to introduce certain important terms. Now what are these important terms? Magnetic intensity or magnetizing force, H, we denote it by H. What it is? It is the magnetic intensity at a point is the force experienced by the north pole of unit pole strength. Remember this thing, that this is the north pole of unit pole strength placed at that point due to the pole strength of a given magnet. So we denote this by H is equals to B by mu, and it is also defined as the magnetomotive force per unit length. Okay, it can also be defined. Now there are certain definitions of these magnetic intensity, but this is the common definition that we have done. First one is the common definition, I mean that you have to remember. Okay, so what are the other definition? It can be defined as the degree or extent to which magnetic field can magnetize a substance. This is also very important, but it's fine, either you remember this definition or either you remember the first one. Now what about the next? It can also be defined as the force experienced by a unit positive charge flowing with unit velocity in the direction normal to the magnetic field. Now its SI unit is ampere turns per meter, that is ampere per meter. Okay, CGS unit is Oersted. Okay, now what is the next term? Next term is the magnetic field strength, or else we simply call it as magnetic field, or else we call it as magnetic induction or magnetic flux densities. So guys, please remember these things, that it's not always we're going to give, or it's not always in the question it will be magnetic field. It can be anything. It can be anything, magnetic induction or magnetic flux density. Okay, what is there? The region around the magnet in which it exerts force on other magnet and on objects made of iron is a magnetic field. So it is a region where other magnet will going to experience its field. Okay, now next thing is the magnetic flux density. The magnetic flux density is the number, the same thing, it is the number of magnetic field lines of force passing normally through a unit area of the substance. You are supposed to remember this thing, that it's passing through a unit surface area. Okay, next is the SI unit is Tesla. We know this thing, you must have done this thing in magnetic effects. SI unit is Tesla, or simply write it as Weber per meter square. This will going to see that from where this will going to come, Weber per meter square. Okay. CGS unit is Gauss, or 1 Gauss is 10 to the power minus 4 Tesla. Sometimes remember this thing, because sometimes it comes at the magnetic field comes in the unit of Gauss. Now next comes is the magnetic flux. Magnetic flux phi. So it is defined as the number of magnetic lines of force passing normally through a surface. So initially in the magnetic field we have considered the unit surface area. Now it's in the magnetic flux, in the definition of magnetic flux, don't have to consider the unit area, it's a complete area you have to consider. So its SI unit is Weber. So relation between B and H, so relation between B and H, we have already done this thing. B is equals to mu H, where mu is the permeability of the medium. And what is magnetic permeability? Mu, it is the degree or extent to which magnetic lines of force can pass or enter a substance, and its SI unit is Tesla meter ampere inverse. And others also we can find it out by considering this relation.
Weber ampere inverse, meter inverse, and this next also. Okay, so what do we have? Why? So B, SI unit of B was Weber per meter square. So it is the thing, phi is equals to B into S. That is, this is the surface area. So if the unit of phi is Weber and B is B, and we want to find out the unit of B, and area is meter square, so therefore the unit of B will comes out to be Weber per meter square. This we can find it out from by this thing. Okay, now let's proceed. And next thing comes is the relative permeability, relative magnetic permeability mu r. Now what is this? It is the ratio of the magnetic flux density in the material to its vacuum. That is, what is magnetic flux density? It is B. So magnetic flux density in any material to its value in vacuum. Now it can also be defined as the ratio of absolute permeability of the material to that in vacuum. So now numerically, how can we write this thing? It can be written as mu r is equals to B by B naught. That is, what is B? B is the magnetic flux density in the material. And what is B naught? B naught is the magnetic flux density in the vacuum. Or else we can define mu r is equals to mu by mu naught. That is absolute permeability of material to its vacuum. Mu naught is in the vacuum. Now let's proceed. Now intensity of magnetization. Now if you look at the intensity of magnetization, we denote it by I. And what does it mean? It is the degree to which substance is magnetized when placed in a magnetic field. It can also be defined. Now we have the certain definition, but remember the definition. First definition. It can also be defined as the magnetic dipole moment M acquired per unit length of the substance. That is M by V. So it can also be defined as the pole strength per unit cross sectional area of the substance. Let's look at how can we define this thing. Now we can write this as, if we take the first one, I is equals to M by V. Now if we take the second one, we know that the magnetic length is 2L. So M can be, magnetic dipole moment can be written as pole strength into 2L. Divide by, if we want to write volume can be written as area into length. So area into 2L, so therefore this will going to come out to be pole strength per unit area. So therefore its definition is fine, that is it can be written as magnetic dipole moment per unit volume, that is this definition, or it can be written as pole strength per unit area, that is this one. So it's perfectly fine using the any of the two. So SI unit of magnetization is ampere meter inverse, and also the SI unit of H is also ampere meter inverse. Okay, so now let's define the magnetic susceptibility. Now it is the property of the substance which shows how easily a substance can be magnetized. So these first definition you have to remember, that how easily it can be magnetized. This is the property. So if susceptibility is more, so its probability of being magnetized is more. That means it can easily be magnetized. So it can also be defined as the ratio of intensity of magnetization in the substance to the magnetic intensity H applied to the substance. So we define it as Cm is equals to I by H. Sometimes we write susceptibility as this, chi m. We call it as chi. So I'll call this as chi. Chi is equals to I by H. Susceptibility has no unit. Remember, what is the unit of I? I has the unit of ampere per meter, and what is the unit of H? It is ampere per meter. So you are dividing ampere per meter. I mean, you are dividing the quantities having the same units. So what you will going to get? No units. The quantity which will be left will not have any unit. Okay, so susceptibility has no units. So relation between, now what is the relation between magnetic permeability and susceptibility? So remember this relation, this is very important relation. Mu r, relative permeability mu r is equals to 1 plus chi m, or 1 plus chi. So remember this thing, this relation is very important. Now magnetic field due to magnetic dipole or a bar magnet. Now if you look at, this is the bar magnet, and these are the these are the north pole and the south pole. So these N and S we can see, and O represents the center of the bar magnet. Now this represents the magnetic dipole moment, and the direction we know, and we have studied that direction of magnetic dipole moment is from south to north. Now if we say that OS is L, that is what do we know, magnetic length is 2L. So what can we write this as? OS is L and ON also L. So therefore, if we want to find out the magnetic field or at any point P which is on the axis, or which is or we call this as the axial point, because this is lying on the magnetic axis. So therefore we are calling it as magnetic. We are calling it as the axial point. So if you want to find out the magnetic field at this point, so and if we say that this point P is at a distance x from the center or O, so this is Bn, and we call this as the Bn, the magnetic field due to the north pole. And so similarly we will have the magnetic field due to south pole, and this can be written, this can be shown as this. Okay, so one thing to note over here, that Bn is more as compared to Bs. Why? Because the distance between the north pole and point P is less as compared to the distance between the point P and S. So what we are going to get? So therefore we will going to get the resultant magnetic field will comes out to be in the direction of Bn minus Bs. So it will be in the direction of M, or it will be towards right. Now if you look at any point Q which is at a perpendicular distance, or it lies at a perpendicular bisector of the bar magnet, and it is at a distance y from the O, so what we'll get? So we'll join these two lines with the north pole and the south pole, and these lines are making, let's say these lines are making an angle theta with this ON and OS. So therefore what we will say, that this represents the Bn, and this represents the magnetic field due to south pole. Now as we can see from this, Bs and Bn are somewhat same because the distance now are same of this point Q. So therefore let's apply the parallelogram law, and what we are going to get, BQ will denote the magnetic field at point Q, that the resultant magnetic field. So therefore what we will get after resolving these magnetic field, we are going to get the magnetic field at point at point Q, and that point and the direction of that magnetic field will be opposite to the direction of the magnetic dipole moment, as we can see from the figure. So this will going to make an angle theta. So therefore what we are going to get, magnetic field. So let's define that what exactly magnetic field at a point on the axial line acts along the dipole moment vector, and the magnetic field at a point on the equatorial line, that is on the perpendicular bisector, acts opposite to the dipole moment vector. So we have already discussed this thing, that on the axial point its direction is this, that is in the direction of magnetic dipole moment, and on the equatorial line or on the equatorial point its direction is somewhat like this, that is opposite to the direction of the magnetic field. Now let's proceed. What do we have? Magnetic field due to magnetic dipole or at a point on the axial line of the magnet can be defined as Bp is equals to mu naught by 4 pi 2mx divided by x square minus L square to the whole square. Okay, what is the point x? This point x is the distance of point P from the center of the paramagnet. And if x is very large as compared to the L we know what is L is the half of the magnetic length. So if L is very less than x, then this can be written as mu naught by 2m, mu naught by 4 pi 2m by x cube. So remember this relation is very important. else you remember this relation. This is the case. So else you remember this relation, 2mx divided by x square minus L square whole square. Now let's take it out the another thing, that at point on the equatorial line of the magnet, after solving it out, we're going to get BQ is equals to mu naught by 4 pi m by y square plus L square to the power 3 by 2. Again, if we apply the case that L is very less than y, then we're going to get BP, or it's BQ. It's actually BQ. So this BQ will going to come out to be mu naught by 4 pi BQ, mu naught by 4 pi m by y cube. So therefore these are the relations, or these are the things we have. So try to remember this thing. So remember this thing, don't have to remember these cases formulas. Okay, so what we have, if due to a small magnet H, or due to any small magnet, magnetic field will comes out to be m by r cube under root 1 plus 3 cos square theta. That means if we take any bar magnet, this is similar to the cases that you must have done in your electric dipole. So if you consider that this is a very small bar magnet and this point P is at an angle, somewhat at an angle theta, this theta, and this is point P. So if you want to find out the magnetic field at point P, so this is the value, this is actually the magnetic field at point P, m by r cube under root 1 plus 3 cos square theta, where theta is the angle between OP and magnetic axis. Now for this case, this is very small, that means 2L is very small as compared to OP, and this P is any arbitrary point. Okay, now let's proceed further towards an example. Okay, if a substance gets magnetized in the magnetic field H, then the intensity of magnetization is proportional to. Okay, what is the intensity of magnetization? It's obviously we have done this thing. So therefore, what is the intensity of magnetization? We have done this thing. Intensity of magnetization, it will come directly proportional to magnetic field. Here magnetic field is given as H. Magnetic field, it's not the intensity, it's the magnetic field B. It's given that it's H. So therefore what we will going to get, it's directly proportional to H. So option A is correct. Okay, what exactly it is? It depends linearly on B. H depends linearly on B. So therefore instead of B, what is given? H. So therefore what we're going to get, it is directly proportional to H. Okay, let's proceed towards the next example. A 10 centimeter long steel wire having a magnetic moment of 3 joule per Tesla. So magnitude of magnetic moment is given to as 3 joules per Tesla. Now is bent to form a part of a circle with opening equal to the radius of the circle. Now initially there was a steel rod of some length L, which we don't know that what is this length L. Okay, yes, it is given that it is 10 centimeter. I'm sorry, this is 10 centimeter given. So this was 10 centimeter. Now this bends to form a circle with small opening, and this small opening is the radius. So what we can say from this thing, this is radius r. So what we can say from this thing, can I write this as 2 pi r, that is the circumference minus the small opening r is equals to complete length L. That means what we're going to get, take pi is equals to 3, so therefore what we're going to get, 2 into 3 into r minus r is equals to L. So therefore what we're going to get, 6r minus r, that is 5r will comes out to be equals to 10, so r will comes out to be equals to 2 centimeters. This is what we're going to get. Now the net magnetic moment is, now we have to find out the net magnetic moment. So we have seen that we got that it's r is equals to 2 centimeter. So if you want to find out the net magnetic moment, net magnetic moment. Let me write it as the net M is equals to, so we don't know what is the net magnetic moment. So it is actually, so we have seen, if this is, let's say this is south pole, this is north pole. So we have seen in the previous example, if we mold this thing in the form of a circle, so south pole will going to come in over here, and north pole will going to come over here. So what do we need? We need, that is, pole strength into R. This is the net magnetic moment. What do we know? We know that what is R? What is R? R is 2 centimeter. We have found out this thing. And what we don't know? We don't know that what is small m or the pole strength. Okay. So therefore what we can, so therefore our aim is to find out what is pole strength. Aim is to find out the pole strength. So what we can write? So we know what is given to us, 3 joule per Tesla. We know the initial magnetic moment when this was a rod, it was M. M is equals to pole strength into the length. It is the product of the pole strength into the distance between the two poles. So therefore this will comes out to be pole strength M into 10. So M, we can write this as capital M by 10. So let's substitute the value of this thing, M by 10 into R, or M by 10 into 2. So therefore this is equals to 3 into 2 divided by 10. Hence the net magnetic moment will comes out to be 0.6 joule per Tesla. According to the option 0.6 joule per Tesla, option B should be the correct one.
So guys, if you have any query, so you can log on to our website www.askIITians.com, and here you will going to find many options, and here you have to choose, among that options you have to choose ask a question, and upon clicking on that you will going to see a discussion board, and on the right hand side you will going to see an ask expert. Here you have to select a category, like if you want to select a category in the physics like general physics, so you have to select general physics. Now here you have the text box, there you can write anything to get answer from the expert. And you can also attach image by clicking on the link attach image, and after that you have to click on get answer to get answer from the expert, and we experts will going to revert back in 24 to 48 hours. Hopefully guys, these terms are clear in this part. If not, then it will be clear as we are going to proceed. So, and moreover we have the next coming part. That part is related to torque, basically more or less related to work done on the dipole. So for that part, stay tuned.